On September 1st of the previous year, a group of 16 researchers made a groundbreaking announcement that sent shockwaves through the scientific community. They released a paper detailing their findings, which challenged some of the most fundamental concepts about the universe. Using the powerful James Webb Space Telescope, these scientists observed distant galaxies and uncovered something truly astonishing. Until this revelation, the prevailing theory in astronomy was that the universe underwent a rapid period of expansion followed by a cooling phase. This cooling phase ultimately led to the formation of the first stars and galaxies, during what scientists refer to as the Dark Ages. However, the galaxies observed by the team appeared surprisingly advanced, resembling our own Milky Way and exhibiting levels of development far beyond expectations. This discovery suggested that these ancient galaxies may have existed long before our own. This finding has profound implications for our understanding of cosmic history, calling into question the traditional narrative of the universe's origins. It particularly challenges the widely accepted theory of the Big Bang as the definitive starting point. While the Big Bang theory posits a specific event marking the beginning of the universe, the discovery of these ancient galaxies suggests a more complex timeline, possibly predating what we currently understand. Before the 19th century, most scientists believed the universe was static and unchanging, with no expansion or contraction occurring. This view was overturned by the observations of astronomer Vesto Melvin Slipher, who noted that certain galaxies appeared to be moving rapidly away from us. Initially, this was attributed to the motion of our galaxy. However, further observations, especially from the Lick Observatory in Arizona, challenged this explanation. The key figure in solving this mystery was Edwin Hubble, who demonstrated a clear relationship. The farther a galaxy was from us, the faster it appeared to be receding. This evidence supported Albert Einstein's theory of general relativity, which suggested that spacetime could expand or contract in accordance with the universe's expansion. By applying the principles of general relativity, scientists came to the idea of a singularity, a point of infinite density and temperature from which all matter and energy originated. This singularity is often associated with the event known as the Big Bang. However, this raises significant questions about what existed before the Big Bang, if anything. Was there nothing, no space, no time? Or are there parts of cosmic history that remain beyond our current comprehension? To grasp this concept, consider the analogy of the surface of a balloon. Imagine the universe as the surface of the balloon, expanding from a smaller size to its current dimensions. As the balloon inflates, objects marked on its surface move farther apart, illustrating the idea of cosmic expansion. The scale factor serves as a measure of the universe's size, much like a ruler measures the dimensions of the balloon. Right now, the universe has a specific scale factor, but in the past it was much smaller. As the universe expands, galaxies and other cosmic structures move farther apart due to the stretching of spacetime. In the future, the scale factor will continue to increase, reflecting the ongoing expansion of the universe. This perspective offers a glimpse into the vast complexity of cosmic history and invites further investigation into the mysteries of the universe's origins. If you slowly deflate the balloon, everything on its surface moves closer together, eventually collapsing into a small flat piece of rubber. This is analogous to the idea of the singularity, a point in the universe's history when everything was incredibly close together, extremely hot, and extraordinarily dense. If we extrapolate the conditions of physics backward in time, we arrive at a moment around 13.8 billion years ago when the temperature and density of the universe became infinite. However, as we begin to wrestle with this idea, it becomes clear that the situation may not be as straightforward as it seems. Current evidence suggests that we shouldn't necessarily apply Einstein's equations all the way back to a singularity. Observations indicate a crucial moment shortly before 10 to the power of -32 seconds after the Big Bang, during which the universe underwent rapid expansion known as cosmic inflation. This period of expansion provides crucial insights into the large-scale structure of the universe, explaining why it appears so uniform and shedding light on the formation of galaxies. Yet, even with the concept of inflation, the singularity remains a difficult idea. Its extreme density and temperature bring quantum forces into play, complicating our understanding. General relativity alone may not be sufficient to fully comprehend the singularity. This early phase of rapid expansion helps resolve some of the puzzles within the theory of how things came to be, but also prompts a re-evaluation of our understanding of cosmic inflation and the origins of the universe. The peculiar nature of the singularity suggests that it might not represent the whole picture. Mathematical singularities often indicate gaps or limitations in a theory. In the case of the singularity, the conflict between general relativity and quantum mechanics highlights the need for a broader understanding. Scientifically, we are still exploring whether there was truly a beginning to existence. Sir Roger Penrose has proposed an alternative framework, suggesting that significant events in the universe's development, including the creation of galaxies and stars, might have occurred before the Big Bang itself. This challenges our conventional understanding and opens up new avenues for exploration. In this broader context, the ultimate fate of the universe remains speculative. As we fast forward through time to infinity, imagining a universe dominated by photons as black holes gradually evaporate, we encounter the immortal nature of these particles. Photons, which follow null geodesics, travel along paths where time and space essentially cease to exist for them. In a sense, they cross the fabric of space-time without experiencing the flow of time. Imagine turning on a flashlight for a brief moment and then turning it off. The instant the light moves away from the flashlight marks one event, event A, and the moment it reaches a certain point away from the flashlight marks another event, event B. The space-time separation between these two events can be calculated using the equation ds superscript 2 equals 0, meaning the photon travels from event A to event B along a path that does not involve any fascinating behavior, as they lack a rest frame and do not possess an individual clock, which aligns with a fundamental principle of physics, the constancy of the speed of light. Regardless of your motion or position, light always travels at a constant speed. However, if photons had a fixed reference point, it would seem as though light is not moving from their perspective. This presents a challenge to our understanding of the speed of light and highlights the unique nature of photons. Maxwell's equations, which govern the behavior of light, exhibit an intriguing property known as conformal invariance. This means that the equations remain unchanged regardless of whether we scale the system up to the vastness of the universe or down to the quantum realm. This suggests that, from the perspective of these equations, both the infinite universe and the minuscule quantum particles appear the same. By applying this conformal concept to the Big Bang, we can envision a scenario where the universe's initial state extends beyond the traditional understanding of the Big Bang singularity. This mathematical approach allows us to describe the beginning of the universe in a way that stretches infinitely backward. Einstein's theory of relativity offers valuable insights into the nature of the universe's origin. It reveals the deep connection between energy and mass, a relationship further explained by Planck's equation linking energy and frequency. This interconnectedness highlights the role of mass in shaping the passage of time. Looking toward the universe's far future, we imagine a scenario where it becomes largely empty, populated only by photons. In this distant future, the universe might resemble the early stages of the Big Bang, suggesting a cyclic nature to cosmic evolution. This idea, known as conformal cyclic cosmology, challenges traditional views of the universe's beginning and end. It proposes an eternal cycle of expansion and contraction, where each cycle mirrors the last. A key concept in this cyclic model is the Hubble boundary, which measures the rate of the universe's expansion. As the universe expands and contracts in an endless cycle driven by dark energy, it represents an eternal and interconnected reality, where the past, present, and future are intertwined. In our daily lives, time flows continuously, shaping our experiences as a series of moments, each one unfolding into the next in an ongoing stream of events. If we were to arrange these moments, each natural event and every occurrence across the vast expanse of the universe would capture the entirety of infinite history. From the chaotic birth of the Big Bang to the formation of stars in the Milky Way, from the emergence of life on Earth billions of years ago to the significant events happening today. These all coalesce into our sense of the present moment. Yet, Einstein's theories of relativity introduce an intriguing twist to this seemingly straightforward idea of the present. According to special relativity, an object's perception of time can vary depending on its motion. This means that moving observers will experience time differently, and they may traverse the fabric of space-time at different points, forming their own unique now. To illustrate this, imagine an object in a distant galaxy billions of light-years away from Earth. As this object moves away from Earth, its perception of the present crosses space-time in a different way, causing its now to shift backward in Earth's history. Conversely, if the object moves toward Earth, its present moment leans into Earth's future, offering a glimpse of what is yet to come. This idea becomes even more intriguing when applied to photons, the particles of light. For photons, there is no distinct past, present, or future. Their now encompasses all of time. Just as we experience all of space existing simultaneously, photons perceive all of time as one continuous whole. This echoes Einstein's famous statement that the distinction between past, present, and future is merely an illusion, though a persistent one. But is there a universal measure of time, a grand clock ticking across the universe? The answer seems to be no. Time is not absolute. It is relative, shaped by motion and perception. So where does this leave us in our quest to understand the origins and evolution of the universe? Sir Roger Penrose's cyclic model suggests an infinite cycle of universe rebirths, complicating our attempts to pinpoint the precise beginning or end of the Big Bang. In this complex cosmic landscape, we might imagine a universe that is continually expanding, creating new universes within itself, a perpetual cycle of creation and renewal. When we combine quantum physics with gravity and introduce the idea of cosmic inflation, we arrive at the notion of timeless expansion, a scenario where most of space is in a state of perpetual expansion, punctuated by pockets where expansion halts. Within this framework, the concept of a multiverse emerges, where every possible scenario or outcome unfolds endlessly. However, recent events, such as the controversial 2014 discovery of cosmic gravitational waves by the BICEP2 collaboration, have cast doubt on certain aspects of these ideas. Initially, it was thought that these waves provided evidence for inflation, but it was later revealed that they were likely patterns caused by light passing through the dust of our galaxy, rather than indicating cosmic expansion. This discovery raised further questions and led to a renewed focus on the fundamental assumptions of the Big Bang theory. Some scientists are revisiting the possibility of the Big Bounce as an alternative to the Big Bang. In this model, the universe's smoothing and flattening do not result from a high-energy quantum beginning but rather arise during a period similar to our current era, where classical physics prevails. This theory suggests that the universe undergoes slow contractions instead of rapid expansion, dismissing the idea of a multiverse caused by quantum fluctuations during inflation. The Big Bounce theory also makes specific predictions, such as a universe devoid of significant gravitational waves due to the absence of energy concentration. Ongoing experiments aim to confirm the presence or absence of these waves, and the results of these studies will not only shape our understanding of the universe's origins but also the relationship between gravity and quantum physics. These discoveries will redefine our comprehension of the universe. If the multiverse hypothesis is correct, our observable universe may be just a random occurrence, making it difficult to understand its fundamental creation. However, if the Big Bounce theory is true, our observations would provide insights into the nature of the universe as a whole, revealing its core principles. The results of these experiments will have profound implications for our understanding of the universe and our place within it.